All right, part two of acids and bases. We're going to look at the other two definitions of acid-base theories. The next one is Bronson-Lowry. Sometimes there were acids that were not a part of an aqueous solution. In other words, they weren't dissolved in the water that still functioned as acids and bases. So Bronson-Lowry talked about um, when a compound or a substance acts like an acid or a base, it's not dissolved in the water. So here they talked about an acid as being a hydrogen ion or a proton donor, and a base was a hydrogen ion or proton acceptor. So we're going to look at that next. So according to the definition that Bronson-Lowry put forward, they said that acids were anything that was a proton donor. Excuse me, sorry, I had a little lapse in my in my thought process. So they were proton donors. So looking at an example of that, I got to go down a couple of slides here. If I look at a Bronson-Lowry acid here, you can see that the hydrogen in the hydrochloric acid is giving away, is donating that hydrogen ion, that hydrogen proton, to the ammonium, producing ammonia, right? And then the chloride ion is left again on its own there. So going back up a couple of slides here, again, Bronson-Lowry defined a substance that donated a proton or that hydrogen ion as an acid. So here we look at a base. So base was the exact opposite. So instead of being a proton donor, it was a proton acceptor here. So in the next slide down here, excuse me, who is accepting the hydrogen ion? The NH3. That NH3 is accepting the hydrogen ion and producing NH4. Okay, so in this case, this is the base as written underneath it, and the hydrochloric acid is the acid. So those are the two definitions for the base and the acid according to Bronson-Lowry. Now here's a couple of more examples. So it's asking us to identify the acid and the base here. So all we're going to do is just look at what's going on with the hydrogen. So the hydrogen ion from the hydrochloric acid is being donated to the water. So, sorry, the kids came into the room, but okay, I already kicked them out. So, the hydrogen ion is being given over to the water. So in here, the hydrochloric acid is the acid, and the water is acting as the base. In the next example here, you can see that the NH3 went to NH4. How did it do that? Well, it had to pick up a hydrogen ion from the water. So the water is an acid. In this case, the NH3 is a base. And then finally, in the last one, you have the carbonic and the water. So here, again, you can look at the number of hydrogens in the H2CO3 went down by 1. So it must have given one of its hydrogen ions over to the water. So this is the acid and this is the base. Okay, and so you'll notice here in these examples here, you see the hydrochloric acid only gave away one hydrogen, the water gave away one hydrogen, and the carbonic acid also gave away one hydrogen. But you'll look at this last example down here, I'm going to highlight it. You'll notice that the carbonic acid actually has two hydrogens that it can give away. And if it can give away two hydrogens like that, it's defined as a polyprotic acid, where hydrochloric acid up here, sorry about that, hydrochloric acid up here only has one hydrogen to give away, so it's called a monoprotic acid. So on the next slide, that's what it's talking about. So monoprotic acids only are able to donate one hydrogen ion or proton per molecule, where polyprotic acids can donate more than one. So they can easily donate two or possibly even three, and there's two examples down here. So the next part is going to focus in on the Lewis acid and Lewis base theory. So again, these were molecules that didn't fit the Arrhenius, that didn't fit the Bronsted-Lowry. So Lewis came in and identified one more way that we could identify an acid from a base for certain compounds. So for Lewis to fit his definition of an acid, a um, a compound or a substance had to be an electron pair acceptor. So if it accepted an electron pair, it was a Lewis acid. And if it donated an electron pair, it was a Lewis base. And I'll have you remember that whenever something accepts an electron pair um, or something donates an electron pair, they're forming a covalent bond. Okay, so here that's what the next slide talks about. In a Lewis-base reaction, there's a formation of a covalent bond. So we're gonna be looking here at two examples where we see this occurring: who's donating, who's accepting. So I went ahead and drew the Lewis structures for these compounds. And in the first example, you'll see that in the Lewis structure for NH3, there's a lone pair of electrons there that's being donated over to um, the boron trifluoride. So here, since the NH3 is donating that lone pair of electrons, it's the base, and that boron trifluoride is accepting the electron pair, so it's the acid, and it produces this compound. In the second example, you have the boron trifluoride that's combining or reacting with the fluoride ion. And here, the fluoride ion is donating, again, a pair of electrons over to the boron trifluoride. It's accepting, so the boron trifluoride is the acid, and the fluoride ion is the base, and you have a production of that compound there. So those are the examples for Lewis acid and bases. This is a good slide here just for review. It gives you the three classifications for acids and bases and how an acid and a base is identified. So in the next slide, it talks about which one of these three classification of acid base do we use? We use Bronsted-Lowry's. That's whose definition we use mostly. It fits a wider range of substances as acids and bases. So we're going to talk about a conjugate acid and a conjugate base. And this slide here talks specifically about a conjugate base. And the conjugate base is what remains after the Bronsted-Lowry acid reacts to give up a proton. So here in this example, you'll see that the hydrofluoric acid is going to donate its hydrogen ion over to the water. And when it does that, it's going to be left with just the fluoride ion. So here, what was my acid now became my conjugate base. So that fluoride ion by itself without the hydrogen ion or that proton now becomes the conjugate base after the reaction is complete. Looking at a conjugate acid, similar process here. The conjugate acid is what's formed when the Bronsted-Lowry base gains a proton. So here you'll see that the water is the one that gained the hydrogen ion or that proton. And when it gains that hydrogen ion or that proton, it becomes an acid. So what was a base on the reactant side now became my conjugate acid on my product side. So here's a couple of practice problems, and we're just going to, here the kind of shortcut way is to look at what happened to the number of hydrogens in the species. So for example here, this HCO3 went from HCO3 to H2CO3. So that means that it must have gained one of these hydrogens from the water to increase its hydrogen count to 2. So in this case, that's the acid, the water's the acid, and there's my base. And on the other side, what was my base now becomes my conjugate acid, and what was my acid now becomes my conjugate base. In the next example, you see here that the hydrogen from the nitric acid was donated over to the sulfate ion, so that produces HSO4, that hydrogen sulfate, and the nitrate ion by itself. So here this was my acid since it was donating that hydrogen ion, that proton. There's my base. What was an acid now becomes my conjugate base, and what was a base now becomes my conjugate acid. So here's just a little bit of information for you to read through, talking about the strength of conjugate acids and bases. I'm not going to go into that into detail. You can read through that, and if you have any questions, let me know. One of the last few concepts here we're going to talk about is amphoteric compounds. An amphoteric compound or substance is a compound or substance that can act as an acid or a base. The most common one is going to be water. So water can, in certain reactions, can act as an acid or a base. Just depends on how strong the acid is that you're dealing with. So here, for example, water acts as an acid in the following reaction. So what's happening here? Water is actually donating a hydrogen ion or proton over to that NH3. That NH3 becomes NH4. So here, this is my acid, this is my base, and on the other side, this would be my conjugate acid, and this would be my conjugate base. The last little topic we're going to talk about here is neutralization reactions. And in neutralization reactions, we're talking about combining a strong acid and a strong base. Strong acids and strong bases only here. And the end result is always going to be water and some kind of a dissolvable salt. That salt comes from the combination of the metal and the non-metal. The metal coming from the strong acid and the non-metal coming from the strong base. So let's take a look at a couple of reactions here. So hydrochloric acid plus sodium hydroxide. What happens here? Well, that hydrogen is going to be donated over to combine with that hydroxide. That sodium is going to react with the chloride ion, and so you're going to get sodium chloride as a salt, and then you're going to get water as a liquid. So this salt is going to be dissolvable, or it dissociates in the water. So that's the first reaction. Second reaction here is the potassium is going to combine with the nitrate, and then that hydrogen is going to combine with the water, or excuse me, with the hydroxide to produce the water. So you get potassium nitrate as a aqueous solution dissolved into that water, that liquid. And then you have the final one that I wrote down was calcium hydroxide and nitric acid here. So you have the base and you have the acid. So that calcium is going to combine with the nitrate to produce calcium nitrate, and then the hydroxide bonds with the hydrogen ion to produce the water in the liquid state. And that's going to do it for this particular PowerPoint presentation. Thank you very much. And if you have any questions, let me know, or send me an email, or send me a message through Google Classroom, or you can attend one of the tutorings that I have on Tuesdays or Thursdays.